Hmm? Oh, I thank you. That's odd. Why did it stop recording? Well, regardless, we've got more time. So we have that happening here. Do we still have any mutations? No. Now we don't. We've corrected all of our mutations. I wish I knew when this stopped recording. That would be really helpful. But either way, we have corrected all of the mutations. So now both daughter cells will inherit a complete copy of the DNA that was in the original cell without any mutations. Let me ask you this. What was it that corrected the mutations?
P52.
What corrected the mutations?
P52.
I want to hear everybody. What corrected the mutations? If I don't have any P53, what happens?
Cancer.
Yeah, and why? Yeah, the mutations can't be corrected, so they mess up this cycle. That's what happens here if we don't have any P53. And that's what this is showing us. Now I want you to turn to a partner, someone seated directly next to you, and I'm going to have you complete some making sense questions here. I'm going to project these on the board. You're going to have to write down these making sense questions because we newly do not have Chromebooks. It's okay. We're gonna have to deal with it. It'll be okay, I promise. So I want you to write down how many correctly paired numbers we have. We had how many substitutions did we have in the top strand?
One.
We only had one in the top strand. Now we have a total of 24 nucleotides on each strand. So what's 24 minus 1? Absolutely. So what was our substitution rate for the top strand? So we had 1 per 24, right? 1 out of 24. How many substitutions did we have in the bottom strand?
2.
We had 2 out of 24. That was our rate. How many correct mutations did we have?
22.
22. I want you to write that down in your making sense questions. Now, after P53 corrected all of these, how many substitutions did we have at the end? 0, absolutely. Now we've got our making sense questions. This is going to ask you about why things were necessary. In question 1, it tells us we started the simulation by uncoiling and unzipping the DNA. I wish I could give you guys this simulation on your Chromebook so that you could play around with it more, but we don't have Chromebooks, so we're stuck. Unfortunately. But I want you to turn to a partner and I want you to ask them, why did we need to unzip the DNA? So turn to a partner and ask your partner, why did we unzip the DNA? Ask the answer. Turn to a partner. So I want you to work with Taija. Can you come up one seat over?
I ain't gonna let you, James. I don't know if you can talk to you. Trying to work with Simon. What? I'm saying one person right next to you. You work with Simon. You go to you. Two. How do you feel? I want to say all.
Oh no, you sound better.
I got none.
Raise your hand if you have a guess as to why we needed to unzip the DNA.
This. What makes sense?
What?
Oh, yeah.
Why do we need to unzip the DNA?
Is it because like it's causing well, the DNA has like cancer on it? Question mark.
So it doesn't have cancer in it? Makes sense. Not what I'm looking for. At the end of this simulation, if I look back here, How many strands of DNA do I have?
Which is what?
How many strands? How many strands do I have?
8, 2,
Right? How many strands did I start with?
1.
I had one strand in the beginning. Now I have two. What did I do?
Subtract. What you divided.
I multiplied my DNA. Right? I doubled my DNA. I had one and I ended up with two. This is how cells can duplicate their DNA and replicate it in order for them to end up with both daughter cells having a complete set of DNA. So I'm going to ask you again. Why was it necessary for me to unzip the DNA? Pardon?
So you could
Yeah, so I could get them out, right? If I had, when my DNA was zipped, these two strands were stuck together. They were one strand. We had one strand, a top row and a bottom row. They were stuck together. If we hadn't unzipped them, could I have added more nucleotides to it? They weren't, they were too zipped. They were already attached to something else. We had to unzip them so that we could attach more nucleotides, more C's and A's and G's and T's. We call those nucleotides. By doing that, we were able to duplicate our DNA. So I'm going to ask one more time. Why did we unzip our DNA? Yes, more nucleotides so that we could double our DNA. Why did we unzip the DNA?
we could double it.
I want to hear everybody's. Why did we unzip the DNA?
Double our
So we could double our DNA.
Why would we need to do that?
Hmm?
Why would we need to double our DNA?
Why would we need to double the DNA? Well, let's imagine this. If I have a cell that wants to divide, I want to take one cell and turn it into two cells. If I don't double my DNA, and I have 46 chromosomes in this cell, I didn't double them, how many chromosomes will my two new cells have?
22.
And then if each of those divide, how many chromosomes will the next cells have?
12.5.
Yeah, well, 12 or 13, right? And then if I divide them again, now I'm going to end up with only 6 chromosomes. That's not going to be enough information for my cells to be able to do all of the things, have all of the proteins, and tell them how to make you. And every time we divide, we have to double the DNA so that both copies can have one full set. That's why we need to double our DNA. And passivation. Once the DNA was unzipped, it looked like this. Explain how did these pairs match up? What does it look like when these pairs match up? Turn to a partner and describe what you see here. These little, I'm going to make this bigger too. We have one that looks like this. We have one that looks like this. We have one that looks like this. And we have one that looks like this. What do these 4 things look like?
Numbers or letters? Shapes.
They are shapes. If I take this shape, these 2 shapes together,
Oh, they can like
what does it look like I could do with them?
triangles. A rectangle.
Actually, I can make a rectangle. I could take this and fill in this space here. So they kind of fit together like
Puzzle pieces.
puzzle pieces, right? Absolutely. Now, these shapes over here do the same thing. If I take these two shapes together and smack them together, they're just like puzzle pieces, just like these two are. So, explain how these pairs match up.
It was like little pieces that fit right in.
Absolutely. Write that down in your making sense sheet. And by that, I mean the piece of paper we're using because the printers are out of toner. And this question asks you, once the DNA was unzipped, it looks like this image. I drew it larger for you here. Explain how these pairs match up. Our next question. When you made a new DNA strand, it was possible for you or the simulation to make an error and choose the wrong letter. How do these mismatches look? That's a visual aid for you. I really want you to turn to a partner and work this one out on your own. I want you to turn to a partner and answer this question on your own. Number three. I'm going to give you about 2 minutes to discuss this with a partner. Okay. Nothing was that.
I don't understand what that says.
What was that?
I don't understand what that says.
We said that when they were matched together, they looked like puzzle pieces. What does it look to get like when they're not matched together? What does it look like when there's a mistake? What does it look like when there's a mistake? Absolutely. Leah, can you come up to the board and draw this for me? I want you to go up to the board and I want you to draw what it looks like when these shapes are not properly matched together.
I draw a word between. Draw a word.
Yeah, sure.
I think so.
Might be easier to use this thing.
And kind of that.
Yep. Draw for me what this is. Oh, it's a cloud.
Not to down the line when the one's right, this also can't catch up that. This is right for it. So can't catch up with it.
Yeah. Yeah, absolutely. That's what it can look like when these mismatches occur. But if these mismatches look like that, what might it do to your cell? We're going to find out more about that in detail. But if your cell doesn't have DNA that's matched together appropriately, DNA makes proteins. It contains the instructions for how to make you. If those instructions get damaged, well, it can result in just about anything, including cancer. We have three different kinds of p53 molecules. We have three different kinds of p53 molecules. I'm not going to have you answer this question in your making sense sheet because unfortunately we don't have time for you guys to all individually come up here and play around on my computer, which is the only computer we have in order to observe this. And hopefully we get Chromebook soon. So I'm not going to have you answer this question, but what you do need to know is that each of these three different versions specializes in fixing other different kinds of problems. That's the only thing you need to know about this question. This last question, I'm not going to have you answer either, but I do want you to spend a moment thinking about this and talking about it with a partner. We first understood these processes in the 1950s. That's how, when scientists first discovered this. How does this information from the model affect how you think about the models that we've worked with in class? And what this really means is, what did you learn and take away from the simulation to help you understand cancer? I want you to turn to a partner and explain it to your partner how these issues with mutations and problems with the DNA can affect cancer. So turn to a partner and in 2 or 3 sentences, describe it to your partner how this works.
Because they destroy the prophase, synthesize the chromosomes, and because I'm done with this.
No, and describe this to your partner. Explain what you do know to your partner.
Will this cause possible cancer? Yeah. Okay, so this is I know how you think. I was gonna say that it was just not protecting you. Still, that was chromosome and lush. So you can higher stage sort of chances to make that person being cancer.
Today,
No. Just throw it so they have chips. Not close. It's not just favorites.
if you can hear me, clap once. If you can hear me, clap twice. I want to describe this a little bit differently for you. Because we're working without you having access to the actual simulation, I'm going to go up on the board and I want to describe this in a bit of a different way. I'm making that quick change. I want you to imagine a book or a reading like the one I'm about to give you. In this reading, we have a whole bunch of different words. The boy tried. Yes. Your DNA works like good. It gives you instructions. It can read like a story. When I have mutations, weird things can happen. If I have a couple of individual, what we call point mutations, where one letter changes, then what I might end up with is something that just doesn't make sense. What does that say?
The Bay Chief Dog.
I changed a couple of individual letters, and now it doesn't really make sense. What is TSE? I don't even know if that's something I can pronounce.
This Bay Cliff Dog.
just a bit of the wall, whatever that is. It doesn't make sense. Imagine that you have an entire blueprint for how to, a recipe that you're trying to cook, and you have a whole bunch of these individual mutations here that change up individual letters all throughout the recipe. How would that affect the ultimate product that you're creating?
You wouldn't know how to do it because you don't understand it.
You don't understand it. You wouldn't know how to do it. I mean, think about it. If I were to add, if my recipe says add 2 tablespoons, and this gets changed to 7 tablespoons, that's one singular letter. That's one number that got changed. If I add 7 tablespoons of sugar to something, it probably won't turn out nearly as well as if I added 2 tablespoons. If I just quadruple the amount of flour that I add to my cake, it's probably not going to taste very good. That's what point mutations can do. And we observed some of these in our simulation. When we had these mistakes happen, if they don't get corrected, then you could copying that mistake over into your new cell. You'd end up with one cell that has the correct recipe for 2 tablespoons, and one cell that's adding 7 tablespoons. One cell that's saying you should divide this fast, and the other cell is saying you should divide this fast. That can lead to cancer. Your DNA gives you the recipe for how quickly cells should divide. If there's mistakes there, well, that mistake can lead to cancer. I'm going to quickly just preface some other kinds of mutations. We're going to talk about these in the next couple of lessons. But as a quick, intro to it, we have other kinds of mutations that can happen as well. Let's imagine a recipe in which we have all of those are called point mutations or substitution mutations. I took one thing and I changed it out for another. There's also addition mutations. And this might look like if I have a recipe that says 2 tablespoons of sugar, my point mutation, my addition mutation might double that word 2. So here we added extra DNA and I ended up with 22 tablespoons. That would be a serious issue. These are how mutations occur, and we were able to see that in the simulation. Now I'm going to pass out a reading for you. I want to pass out this reading, one to each person. Cardian, can you do that for me? It's 2-sided. You are going to partner read in this. And you are going to partner read with this reading. So I need your heads up. Decide which of you is going to read first. You're going to go paragraph by paragraph. For my student who unfortunately is all by themselves, it's easy. If you could read by yourself, I'd really appreciate it. I'm going to give you about 2 minutes, 3 minutes to read this. You're going to alternate by paragraph. So raise your hand if you're reading first. Perfect. Now, alternate by paragraph. If you're reading first, you're reading that first one. You have 3 minutes to begin, starting now.
Slightly increase this one is a big one or now conflict like maybe this is a chromosome. This man is an organized now. DNA goes confidence, chromosomes are DNA goes like most is made up, smaller parts of the nucleotides. DNA reduce or a portion of DNA with a single nuclear highlighted by the red box. A portion of the same DNA, therefore, really just the genetic code of their mind doesn't have a nucleus for this. We have DNA. The nucleotide is made of infrastructure, single and proteins, a base. Let's say, we're not going to be talking about the DNA, they usually referring to DNA, they usually referring to as bases. Other parts are the nucleotide staying on the other part of the but the base can take one more form abbreviated with several C, 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 D, and C. On certain or being honest because compound search. On certain bases are attracted to each other. Causing complementary together these concepts and teach attracted to stage period. Together these combinations are known as complementary base. Humans have more than 3 billion pairs chromosome has phase of mitosis. The DNA is making a copy of itself. DNA. The DNA is making a copy of itself. Also, DNA replication. So when the DNA strand is exposing the nucleotide and the nucleotide to go with their complementary nucleotide base. In our simulation, we will military base. A section of DNA that was 2 4 bases long. Your cells can be concentrated to the 2.3. Okay, when area states of having houses or mutations in the center, these are required. These are snake and sick. And so, here for scenes and days, you have retained to navigate channels to be new sources of things. Definitely not that thing.
Perfect. Thank you. If you can hear me, clap once. If you can hear me, clap twice. Raise your hand if you can summarize for me in a sentence or two the first paragraph. What's the first paragraph? That's a really important point. All of our DNA taken together is similar by 99.9% to every other human on Earth. 99.9% of our DNA is identical between all humans. Are there any other main points that we need to get out of the first paragraph? Okay.
DNA only appendices into chromosomes that are cell division.
Absolutely, that's a big point. DNA condenses into chromosomes during cell division, but most of the time it looks like the 2 diagrams you have on your sheet right below. Like a urn. Now, we have DNA replication happening. Do you see how that's bolded later on the other page? DNA replication is the process by which we
What's the question?
What's the process of DNA replication? And in that, we do what with our DNA?
Oh wow.
You copy it and you make another copy. I want you to look through and find all of the words that are bolded. Those are the new terms that are involved in this DNA replication. I do. And then I want you to shout them out. What's the first one? Nucleotides. Can you say that? Absolutely. Nucleotides. Traylon, what's the nucleotide? DNA is a large molecule. What's a nucleotide?
Oh, maybe the sugars, also in the base.
Mm-hmm. A sugar, phosphate, and a base. If I made up. What's our next folded word?
Base.
And cardigan with the base.
One part of the nucleotide.
Just one part of the nucleotide, absolutely. What's our next folded? Well, this was more of a phrase.
DNA replication.
Not yet.
Oh, Inter.
A, T, G, and C. We'll get to complementary as well. Those are the 4 different kinds of nucleotides that we have. What's complementary?
The A is attracted to the T. The T is attracted to the C.
We call them complementary because they go together. And we saw this as an example during our simulation. We saw how the A and the T fit together appropriately. We saw the G and the C were fit together like puzzle pieces. Those are called complementary base pairs because they fit together. We have more than 3 billion base pairs in the whole genome. Now, that gives you all the information that you are going to need in order to understand these main topics that we're dealing with throughout lesson 5.